Okay, in this video what I'm going to do is I'm going to build upon the LED response that we just derived an equation for and show you how a little bit more about the response of the LED. It turns out that this saturating optical power is one characteristic, but another characteristic which is important and we'll outline is the frequency response. Okay, so generally speaking, we're going to have our optical power output given as a function of the input drive current, and we're going to have some maximum output power, and we're going to have a response that looks linear up until that power, and then at least in a simple model quickly saturates or instantaneously saturates to this maximum output power. And so what we can think of, so this is equal to the drive current, and this is the optical power out. Of the LED. And we go ahead and make the picture of a normal LED type of circuit diagram and just put a circle around it, and sometimes we go ahead and put an arrow with a photon coming out, okay, maybe an HF wavelength coming out of that. So there's the circuit diagram for an LED source. Essentially the same circuit diagram for a laser diode, I think. Okay, so let's go ahead and consider, at least for the moment, the analog case where we're going to go ahead and put a sinusoidal input into this thing. Okay, so at low frequencies, I'll go ahead and start with the assumption that this is a low frequency right away, and that will give you the hint that at high frequencies something different happens. The output power is going to equal the drive current times the slope delta P over delta I. Okay? And let's assume that our drive current is equal to a DC value plus some signal power, or some signal, I don't know what to call it, SP for lack of a better, times the sine of omega t. So this is a sinusoidal input with DC offset and frequency F is equal to omega over 2 pi. Okay, and we're just going to refer to omega as the angular frequency. And so the optical power, we're going to go ahead and write its output as PDC plus PSP, that's why we're using the subscript SP for signal power, times sine of omega t. Okay, and I guess you can write that PDC is IDC times the slope, and P signal power is I signal power times the slope. Okay, and this works at low frequencies where omega is less than some cutoff value of some sort. And in other words, and this also works if the PDC plus PSP for, so this holds for the case of low enough frequency, and it also works in the case that PDC plus PSP is less than or equal to P max. Okay, you can see that if we try to drive the thing above that value, then we'll have a problem in that the output will be severely distorted. Okay, I'll go ahead and draw a couple quick sketches of what can happen to the output if we overdrive it. Okay, so these sketches are kind of fun to make. We can go ahead and drive current to optical power out. We can go ahead and make a sketch that shows the drive current versus P opt like this, and what we'll do is we'll plot the input current sort of a funny way, sideways, where we have IDC here, and we're going to go ahead and plot versus time now in this sideways plot, and we're going to go ahead and make a sine wave like this. And you can see that I have kept, and let's see, the this value of the current is IDC plus ISP. Okay, the signal current. Okay, and then this value is correspondingly IDC minus ISP. And you can sort of just take this point here, and you can take this DC current and say, okay, that DC current is going to give this DC power. And now we're going to go ahead and plot the power out versus time here. And this particular DC current is going to give you this particular DC power out. So this is going to be PDC. And then the max and the min are also going to work out just fine. So this will, in the case I've drawn here, where we're kept everything less than P max, what we're going to have is a sine wave on the output that's undistorted. If, on the other hand, we so this is this one's the output is not distorted. If this section were not perfectly linear, the output would not be where we have perfectly linear response, and we don't drive it too hard. We don't drive past P max. Okay. On the other hand, if we were to go ahead and okay, I've got a new heading on this one. If we were to drive this thing too hard, if we take our input current versus time, and now we're going to plot our output power versus time here, and if our input goes above the threshold, then we've got a problem. Okay, so what will happen is this DC will be transferred just fine to this DC value, and down on the low end we're fine. We've got linear response. But on the high end we've got a problem, because anything that comes from here will all get smashed down in some sense. And so what we're going to see is we're going to see it go up And instead of going nice like this, we're going to see it with a flat top like that. Distorted output. So this is the idea on the distortion where P DC plus PSP is greater than P max. Greater than, let's just say, strictly greater than. Okay? So this can be a problem. So this is the basic idea of driving an LED. You can distort your output if the response isn't perfectly linear. You get something slightly differing from a sine wave on the output also. And these are the equations that you can use to do that. One of your homework problems actually requires you to figure out what the current is when you have your P max. Okay, and so that's easy to do using the slope. Okay, so your I max is easy to figure out using this delta P over delta I slope. Okay, hope that helps. Thanks.